and psi of x, I think they do like something like this, e to the kappa x plus d e to the minus kappa x. Again, I mean, and this is in the barriers. And the idea is that what we want to do is we want to try to see if we can actually solve the Schrodinger equation for this picture. And it turns out that you can because everything is flat. It's like a flat bottom well or barrier like this. And so I think for a given value of energy, you just literally are going to get E is going to be h bar squared k squared over 2m in this region here. But then what's going to happen is that you'll have V minus E is going to be h bar squared kappa squared over 2m, I think, in the barrier. So in other words, because we'll assume that E is less than the height of the barrier, I think, and I believe is one of the assumptions that's made. And so then the question is, okay, but we want everything to match up at the boundaries. So you have to satisfy the boundary conditions in some way. And so when you go through that exercise, you end up being able to come up with some kind of analytical expressions that relate to how k and kappa relate to each other. And then what happens is that you end up, when you actually plot to see where is it possible to have a solution, you find, oh, if I look at, well, what energy levels allow you to have a solution, which ones don't, you find that there are, in fact, some regions where you do not have an actual allowable solution. And so we say, okay, those are the actual band gaps in this so-called Kronig-Penny model. And so it's only certain values of k related to certain values of kappa, I guess, that allow you to get, that actually get propagating solutions, allowable solutions. And so now, if you plot energy versus k, before, we just had h bar squared k squared over 2m for a free electron. Well, what happens now is you end up with these little gaps that open up in that plot. Now, there's another subtlety that comes into play, and that is that in these types of periodic crystals, there's a theorem called Bloch's theorem where you can represent the wave function as a product of this kind of term, e to the ikx, times a periodic function of x. And what actually ends up happening is that you could actually show that when you look at these higher values of k, everything kind of folds back into something that's called the first Brillouin zone. I'm sort of condensing about half a semester of condensed matter physics or solid state physics into like a few sentences right now at the moment. And so when you fold everything back into the first Brillouin zone, if I started out with, let's just say a free electron gas that looked like that, energy versus k in a 1D scenario. If I started to fold, even just taking this case, you could actually, well, if I had it in a lattice, I could even take this guy and fold, I get up to some point, maybe, oh, okay, where would you fold that back? It would be when k is equal to pi over I think it's called the unit cell. Yeah, just your unit cell, the size of it, let's say it's A is the unit cell. I can't remember if I think it's pi, plus or minus pi over A. So that would be called the first Brillouin zone. So what would happen is that this branch would end up folding back over here like this. And then I guess it keep on going until you get up to here. But what happens is that right at the boundary is where you get the gaps opening up typically. And so you have the band gaps typically opening up right here. So you have the band gap here. It's supposed to be symmetric. Sorry, I didn't do a very good job of drawing it. So at any rate, what you end up with, it should be right, more or less, but what you end up with is a gap right at the, what's called the first Brill-1 zone boundary. I don't even know if they mention that term in Thornton and Rex. First, if I'm spelling this correctly, Brill-1 zone. But it actually doesn't matter, but the idea is that, because you could also write it where you just keep repeating it as a function of k and just have these gaps keep going up. That's the way they show it in the slides, in the Thornton and Rex slides. And anyway, the idea is that in the case of a semiconductor, so if you had a metal, it would actually behave pretty much the same way as long as, let's say this band down here, or whichever, any of these bands, if there's some band that isn't quite completely filled up. So the idea is that, okay, if I didn't quite fill it up, wherever the electron sort of filled up to partially, that would be the Fermi surface, so it'd behave like a metal. But what happens in a semiconductor is that you fill up all these guys up to here, and then, boom, you're kind of stuck. It's like the Fermi sea is just stuck there, because you have that big band gap right there. And so the only way to conduct a current, unless you dope it, which is a whole other thing we'll get into maybe later, is to actually thoroughly excite electron holes by exciting electrons across the band gap. So you create an electron here and a hole down here. So let's be in. And so then by thermally or optically or whatever means, creating electron hole pairs, if you do that, then of course then the semiconductor is able to carry a finite current. And so this is probably a good point for me to go ahead and stop for today, but that'll just give you kind of I hope, a little bit of a heads up. And on chapter 11, I'm hoping that something will be working, or maybe necessarily use this projector, so that I can kind of scroll through a few of the slides in Thornton and Rex. Again, we're sort of trying, it's impossible to get into too much detail, because it would be like a couple of semesters worth of condensed matter and solid state physics, plus decades worth of work on band structure that people have done, a whole thesis project at a minimum of doing band structure calculation to get into every detail, but at least to give you a bit of a flavor on some of the ideas about, okay, why do some materials act like a semiconductor, metal, or an insulator? What's an insulator? An insulator you can think of as just a semiconductor, except the band gap is really, really huge. And so therefore, it's really difficult to create electron hole pairs. So an insulator is almost exactly the same as a semiconductor, except it has a much, much bigger band gap is the essential idea. The other key idea, of course, is that the electrons are filled up to the edge of that band gap. And this down here is typically called the valence band, and then this would be called the conduction band. If you excited electrons across the band gap, then they're able to conduct, so that's called the conduction band when we talk about semiconductors. Okay, so I think that's probably enough for today. And so Wednesday, I hope to go over a little bit more than about semiconductors.